I'm gonna start this video by recalling a theorem we proved in a previous lecture. I'm gonna put the description in the description below the link to the video lecture, and it's the theorem that talks about the number of elements of order D in a cyclic group. So let me quickly remind you what the theorem said. So if you have a group that is cyclic of some order n, so finite order, and if you have a divisor D of that n, the order of the group, then the number of elements in G of order D is phi of D. So with this is the Euler function, the one we talked about that video. Again, I'm going to put that video in the video description for this lecture. Now, that's what I want to point out, the statement, but one more thing in particular is in the proof of that theorem, what is important about that, one of the important things about the proof was this, that if you take H, that is the unique subgroup of G of order D, because there is a unique one, because we are talking about a cyclic group and a divisor. For H divisor, there is a unique subgroup of that order called H. Inside the proof of the theorem, we prove that every element of order D is a generator of H. So if you go back and look at the proof of that theorem, this should be something that we proved there inside that theorem. Now, I'm going to use this fact to go over an example, again, an example about the application of this theorem here. So let me go over the example. So let's look at this group. So consider the group U54 with this binary operation. Now recall that the U54 is the elements of this are all the elements between 1 and 53 that are relatively prime to 54. And the binary operation here is multiplication modulo 54. This is also an example that we saw in a previous video. I'm going to also put the link in the video description again for the example, this example we talked about. Now, if you look at the elements of U54, that are all the ones that are relatively prime to 54 between 1 and 53, that is going to be this list. So is this list of 18 elements that you see here, that will be U54. And again, this multiplication is modulo 54. Now, another observation that we made in the video 2 was that U54 is cyclic and is generated by the number 5, which is one of the elements right here. So this is one of the generators of U54. Now, how do you check that? Well, you have to go ahead and take powers of this element and realize that all the powers of this element 5 are going to give you all of the list that is here. That is, of course, modulo 54. So because that is the order of an element here is the same as the order of the group, this set has 18 elements, so is also the element 5 of order 18. Now, what we want to do in this example is the following. We want to describe all the subgroups of U54 and their generator. So for each, we're going to talk about each subgroup of U54, and also for each subgroup, we're going to describe or list the generators of that subgroup. So we're going to, of course, to do this, we're going to use the fundamental theorem of finite cyclic groups. So that theorem has 3 parts. I'm going to put that link also in the video description. So for that theorem said that every group of this one, because this group is cyclic, we know that we can apply this theorem, the fundamental theorem of finite cyclic groups. Because of that, that means that theorem tells us that the divisors of the order 18, so the divisors of 18 correspond to the subgroups of this group. So that means, recall, for every divisor D of 18, the subgroup that was correspond to it is the one generated by A to the n divided by D, n is the order of the group, D is a divisor of the order, and A is one of the generators of the cyclic group. So in this case, A will be 5, for example. Now, to look at the subgroups, we have done this already in another example, but in this case, we're gonna expand a little bit more on that example, which is for every subgroup, not only we're gonna say what the subgroup is, but also talked about the generators. So we first go ahead and look at the divisors of 18, that's the order of the group. And the divisors of 18 is all this list that you see here. So it's 1, 2, 3, 6, 9, and 18. There's 6 divisors in total. So each divisor is going to give us a subgroup, and we're going to talk about the generators for each subgroup. All right, so let's start with number 1. So for number 1 here, so the subgroup that for divisor number 1, again by the theorem, that subgroup, I'm going to call it H1. Here this is just a notation. So H1 is going to be the one generated by A to the n divided by D. Remember that is here. That is part of the theorem, the fundamental theorem of finite cyclic groups. So n here is 18, D is 1, that's the divisor. So as the one generated by 5 to the 18. Now 5 to the 18 is the identity of the group because it's the element raised to the order of that element. So that's going to give me 1. 1 is the identity of the group. And so that was going to give us that the one generated by 1 is just 1. So if you think about it, multiplication by 1 gives you 1 modulo 54. So this in this case has only one generator. We know that. We also, I'm going to point out something here. The generators of this group, of this one here, is phi of D. So is phi, let me write it down here, is phi of 1. Because corresponds to the divisor 1. So phi of 1 will give you the number of generators of that subgroup. But phi of 1 is of course 1, so we only have one generator. I mean, we don't have to do this computation to realize that is 1. That's just to point out that that's going to happen if you actually want to find the number. Okay, so 2 is another divisor. Well, because that's I'm looking at this list right here. So this one. So we're going to go through this list and all of those numbers. So for the divisor 2, so the subgroup I'm going to call it H2 is going to be 5, the generator of the group, to the 18, that's n divided by the divisor 2. So that's 5 to the 9th power. Now remember here we are in U54. So in U54, let me emphasize that. In U54 here, this group, the binary operation is multiplication modulo 54. So when we talk about 5 to the 9th power, is that modulo 54. If you do that, modulo 54, you get 53. So it's the subgroup generated by 53. Now, this H2 is going to have 2 elements. So the divisor, this divisor here, is actually going to tell you the number of elements that you have in the subgroup also. So I have 2 elements. That is the identity. The identity is in every subgroup. So it's 53 to the 0 and 53 to the 1 power, first power. 53 to the second power is going to give you again 1 because this has order 2. Now, by theorem, this is going to have phi of 2 generators because it's going to be the number of elements of order 2 that we have here. That's why I'm using, in this case, I'm using the remark. The generators of this group is the number of elements of order D. So D here is 2, so it's phi of D, phi of 2 generators. Phi of 2 is 1, so we have only one generator, and of course that will be 53. So that would be 53 is the only generator of H2. Let's do the same for 3. Now this is going to get more interesting as the number gets a little bit bigger. So for the first two, H1 and H2, it doesn't say much. So let's see what it says about this one. So for the divisor of 3, I'm going to call it H3. So in H3 will be the one generated by 5 to the 18 divided by 3. That's always because of the theorem, the fundamental theorem of finite cyclic groups. And that is 5 to the 6th power. 5 to the 6th power is 19. Remember, we are doing this computation modulo 54. So you take this power and then divide by 54. The remainder will be 19. You start taking powers of 19. We know we're going to get 3 elements. So 19 to the 0 power is 1, to the first power, to the second power. So that will be all the elements. And then you simplify here. 19 squared is 37. That's modulo 54. Now, this also, we can know exactly how many generators we have by using the theorem I described at the beginning. So it's going to be phi of d. Phi of d will give me the number of generators of the subgroup. So it'll be phi of 3. Phi of 3 is 2. If you compute that using the fact that 3 is a prime number, so it's going to be 3 minus 1. So we're going to have 2 generators. And in this case, it's easy to check what are the generators because in this case, the identity cannot be the generator because the identity just gives me 1 if I start doing the binary operation. So these two, 19 and 37, they will have to be the generators because we have 2 and they have to come from the subgroup. So they are 19 and 37. That's what we have here. So let's see, this is a little bit more interesting case. So for the divisor 6, we can have a subgroup of U54. I'm going to call that H6. So this subindex here, just for this notation, is going to denote the divisor. So H6 will be the subgroup that corresponds to the divisor 6. So same thing as always, by the fundamental theorem of finite cyclic groups, is the generator of the group to the n number of elements of the group divided by whatever the divisor is here, 6. It's going to be 5 to the third power if you do that division. Again, doing this modulo 54, that gives you 17. Now, this group is going to have 6 elements, and that's going to be all coming from powers of 17. So you start taking powers of 17. The 0 power, the first power, the second power, up to the 5th power. If you do the 6th power, it's going to give you again 1, because this element has order 6, because the group subgroup has order 6. So you take powers of the element here, which is the generator, is this. Now remember again, this is all modulo 54. So if you simplify all of this modulo 54, it will give you in this order, it will give you 1, 17, 19, 53, 37, and 35. So I'm going to organize this in, of course, increasing order of the numbers. So H6 will be this one here. Now, I can know how many generators I have because I have the theorem. The ones that tell me how many elements of each order, all the elements of order 6 will be generated for this group. So H6 will have phi of 6 generators. So that will mean that I have to compute this, and if you actually do the computation, just express this number 6 as the product of 3 and 2 and use properties of this Euler function to get the number 2. So if you do the computation, you get 2 here. So that basically says we have 2 generators here. Now in this case, it's a little bit more difficult to tell what the generators are, but we also know what the generators of a group are if the group is cyclic. This group or subgroup is cyclic, so we know exactly what the generators of a cyclic group are powers of these this element where the exponent is relatively prime to 6. So the generators of H6, because it's cyclic, have the form 17 to the k, where the k here is a natural number whose greatest common divisor between that number and 6 is 1. Why 6? Because 6 is the number of elements of the subgroup, and k is between 1 and 6. So in this case, the k's that are relatively prime to 6 and are between 1 and 6 are only 1 and 5. So 2, 3, and 4 do not have greatest common factor between k and 6 is not 1. It's another number. So it's only 1 and 5. So the generators here will be of this subgroup will be 17 to the first power corresponding to this exponent and 17 to the 5th power. So if you simplify this modulo 54 again, you get 17 and 35 for this one. So we have exactly 2 generators. So in this case of this list, this one, the 17 and the 35 are the generators of this subgroup here. Now let's do a couple more. So the subgroup that corresponds to this divisor number 9. So I'm going to call it H9. That's the 5 to the 18 divided by 9. Again, this is the generator and divided by the divisor. So that's 5 squared. If you do the computation here, 5 squared is 25 modulo 54. That's not something that you need to simplify, actually, just for 5 squared. This group here, or this subgroup, this is going to have order 9. So it's all powers of 25. So it's 25 to the 0th power gives you 1. And all the way to 25 to the 8th power. So I have 9 elements in total because this corresponds to the divisor 9. that remember all of what we are doing here is only true if you are inside a cyclic group. If it's not cyclic, the divisors do not correspond to subgroups. So that's not the case, but this is cyclic, so we can do that. So again, you can do all of this modulo 54. So we're gonna simplify like this. So this order that is here is exactly this order of elements 1, 25, 31. So 31 here corresponds to 25 square modulo 54, and so on for these other ones. You see, these are not in increasing order, so you just do it in the increasing order here. So these are the elements of the subgroup. So these are the elements. Now here we can tell how many generators it's going to have, because the generators are the elements of order 9, because this subgroup has order 9. So H9 has phi of 9 elements that are the generators, and phi of 9 is 6. How to compute this one? Then use the properties of the Euler phi function. This is 9 is 3 squared, and use the property for a power of a prime. So if you do that computation, that's gonna give you 6. So this H9 is gonna have 6 generators, and then again, the way we look at the generators is how are all the other generators, as you choose one of them, which is 25, and any other generator has the form 25, that generator to the k, where this k is the greatest common factor between this k and 9 is 1. Why 9? Because that's the number of elements in the group, and k is between 1 and 9. Now if you go through the list of the natural numbers that satisfy these two properties, this one relatively prime to 9 and between 1 and 9, those natural numbers will be this list here: 1, 2, 4, 5, 7, and 8. So the generators will be those powers of 25. So it's going to be the generators of this. So will be 21 to the first, second, fourth, fifth, 7, and 8. That's corresponding to this one. And again, this is all modulo 54, so you get this. So these are the generators of this subgroup here. Finally, for the last one, so the subgroup of that correspond to divisor 18, so it's going to be, let's denote it by H18. So it's 5 to the 18 by 18, so there's 5. This is exactly the group itself, the U54. And H18 has phi of 18 divisors, because it's the generators of this are exactly the elements of order 18, which is phi of d. And if you do the computation, phi of 18 is 6. Again, just do this one as 9 times 2 and apply properties of the Euler function to find that value. So that's going to give us 6 generators of this group. We actually have done this already in one of the videos before. So let's go through it again. So it's going to be the generator is 5 to the k, where k has no common factors other than 1 with 18, and k is between 1 and 18. So k in this case, if you look at the naturals that satisfy these two properties, k will be the numbers 1, 5, 7, 11, 13, and 17. Those are the numbers exactly that satisfy this condition. And this one here, that's going to give me the exponent that will give us the generators of U54. So you do the same thing, you take powers of 5 with these exponents, simplify modulo 54, and then if you do all that computation, it's going to give you these elements here. So 5, 11, 23, 29, 41, and 47 are the generators of this one, which is 6 of them, because we knew already the number of generators that we have. Alright, so one more thing I want to do about this subgroup is look at the subgroup lattice. So the subgroup lattice, remember, is just a picture that gives a relation of inclusion between all the subgroups of a group. So we have U25, which is the whole group itself. Now U9 and U18, if you just go back, this one, U18 is this one. So this is H18, because that's going to be the whole group. And the other ones are going to be H9 is of course included there. H6 is also included in the whole group, but it's not included exactly in H9. If you look at the elements of H6 and H9 in this list, in this video, you're going to see that this one is not included in this one and vice versa. So we put it in separate branches of the lattice. Now H3, which is also one of the subgroups, is included in both H6 and H9, so that's why we put these lines here. Remember, these lines represent inclusion. Now H2 is included in H6, but it's not included in H3 or H9. So if you go and check the numbers, that's gonna be true. And then finally, H1, which is just the trivial, this one here is gonna be just the trivial group generated by 1. In this case, that's the identity. It has only one element. So that is the subgroup lattice of the subgroup of this group U25. Now, I didn't have to do this at the end, but I wanted to give a total description of the subgroups of U25. So with this theorem, not only we have all the subgroups, we can know what all of them are, we can also know what the generators of each subgroup are. So this is a complete description of the subgroups of a cyclic group. Again, this only works for cyclic groups. If it's not cyclic, this thing is a lot more complicated. All right. So that's all I have to say for this video lecture. Take care and good luck.